Okay, so first of all, thanks a lot to the organizers for inviting me to give this talk today. It's a pleasure to virtually be here. To everyone else, thanks a lot for tuning in, and good morning, good afternoon, or good evening to wherever in the world you might be. So today I'm going to tell you about the status of the galactic center gamma ray excess. Now, this is a signal, on my turns. This is a signal that has been very controversial. So the interpretation of this excess has kind of oscillated back and forth several times in the more than a decade now that we've known about its existence. So today I'm going to tell you about some of the latest developments in our understanding of what the excess might be, but I'm also going to give you a bit of a introductory background as to what the properties of the excess are and what we've kind of come to know about it. I'll tell you about the different hypotheses we have for the excess, how you can tell them apart, what the latest developments are here, and I'll also tell you a bit about systematics and why these are really important for understanding what's happening in these galactic center excess studies. And then towards the end, I'll tell you some ways forward. Okay. So what is the galactic center GeV excess? It's a highly statistically significant bright excess in gamma rays. So it was detected by the Fermi Gamma Ray Space Telescope. In fact, it was found first by two theorists, Dan Hooper and Lisa Goodenough, back in 2009. And its spectrum is peaked at around a few GeV. So this is the figure that you can see on the right. You see this is just a residual map, something that's very bright towards the center of the galaxy. Okay. So features do we think it might have? In terms of its morphology, it looks like it's something that's approximately spherically symmetric around the galactic center. So you can see something like the figure here. It scales like an inverse power law, so over r to the minus 2.4 roughly, extending out to around at least about 10 degrees from the center of the galaxy. So the really interesting thing here is that it can roughly fit a standard dark matter profile, so just the NFW sort of profile. There have also been some interesting recent papers saying that potentially the morphology of the excess might be more like the stellar bulge. So that has the morphology shown on the right. These are the papers at the bottom, and I'll speak just really briefly about that later. In terms of the spectrum of the excess, the shape appears to be uniform throughout the inner galaxy. So what you see on the bottom left is just the center of the galaxy broken up into different pieces, different regions. And then on the right, you see the spectrum in a number of these different regions effectively looks the same. So it seems to be pretty much the same thing throughout the galaxy. In terms of its spectrum as well, together with this intensity, the spectrum is well fit by a tens of GeV dark matter particle annihilating to hadronic final states. So the really interesting thing here, so what you see on the right is for different dark matter masses and different annihilation cross sections, which is the y-axis, you see this is pretty close to the thermorelic cross section. And so for some of these different final states or different topologies, different spectra, you end up getting something pretty much on what you would expect if thermal dark matter is what's giving you this excess. So this seems really exciting. So this looks like it could be a signal of annihilating dark matter, in that the morphology could be consistent. It seems like it could be approximately spherical. It extends well out of the center. It has the intensity of thermal particle dark matter, being that it can match the thermal relic annihilation cross section. And the spectrum is consistent in that it's invariant with its position and shape. And the spectra can be fit really easily to really minimal sort of particle dark matter models. So if this really were a dark matter signal, it would be the first evidence that we have of dark matter standard model interactions. So far the evidence we have for dark matter just comes from its gravitational interactions. We don't know if it even interacts with the standard model at all. So if it turned out that's what we actually were seeing here, we would learn so much about dark matter. And this is really one of the most pressing open questions of modern physics. What is the fundamental nature of dark matter? So maybe this is something we have right in front of us. Maybe we already have a dark matter signal. This is really something we want to get to the bottom of. Okay. So I just told you a little bit about how this signal looks like it could be dark matter. But of course, there are other hypotheses as well. And the leading alternative hypothesis is that it's coming from something called pulsars. So pulsars are rapidly spinning neutron stars. I think the best argument that you can make for pulsars explaining the excess is that they kind of roughly match the gamma ray energy spectrum for the galactic center excess. So these are the millisecond pulsars in particular. So pulsars appear as point sources to Fermi. So this just means that they have angular extent below detector thresholds. So I'm going to be using the phrase point sources rather than pulsars, I think, for the rest of the talk. but you can keep pulsars in mind as a sort of physical manifestation of these point sources. Right, so you might wonder, if I'm saying that pulsars might be the galactic center excess, why don't we just look at pulsars in the center of the galaxy, because pulsars are something generally we can observe, and then just measure their spectrum, look at the morphology, and then just call it a day. The problem with this is we've tried to do this, and we actually haven't found any pulsar that seems to be the galactic center excess. And the sort of ones that you'd want to try and see are ones that are really bright. So this is a class of point sources called resolved point sources. So they're bright enough to be individually detected. And any of the ones that we can individually detect don't look like they're the galactic center excess. So the class that we want to consider as the potential other hypothesis compared to dark matter are unresolved point sources. So unresolved point sources are too dim to be individually detected, but you could imagine you have a lot of these unresolved point sources that collectively, when you add up the flux of a lot of really faint things, could explain the galactic center excess. So we want to answer the question, is the galactic center excess dark matter, or is it these unresolved point sources? Okay. So how do we distinguish these two different hypotheses? Thankfully, they have a particular property that makes it easier to tell them apart, being that the counts of gamma rays that you get from point sources exhibit different statistical behavior compared to those that you have from annihilating dark matter. So you can see this in the figure in the left. This is just from simulations what you might expect dark matter to look like as the galactic center excess. So you see, if you have dark matter in a smooth sort of continuous halo, you expect roughly a smooth signal of gamma rays. Compared to if you have point sources, you have an image that looks a bit more like on the right. So the image looks more clumpy. And this is because you could imagine in a given pixel of the sky, you have no pulsars, so you have no gamma rays. And then in a different pixel, you might have several point sources giving you lots of gamma rays. So the pixel to pixel variance is much higher than the smooth case you have for dark matter. So we want to go hunting for smooth signals or sort of more clumpy signals. And there are two different methods that have been used to do this. So these are sub-threshold searches. So one method is called template fitting. So the way this works is you have a full sky of gamma rays, and you want to build up a picture of your gamma ray sky by modeling individual components that all add up to give you the total number of gamma rays. So these can come from some model you might have, some ansatz, or some catalogue of things you've already actually measured. So I've just shown some example combination of templates. So these are the different components that you might have. And you can add these together and you can all float them in a fit and just see how much flux wants to go into each different component. So really importantly, we want to know the answer to the question for the galactic center excess sort of morphology, which is shown on the far right. We want to know, does the fit want something that's smooth or something that's clumpy? And if it looks more clumpy, that's probably point sources. If it looks more smooth, it's a lot of really faint point sources, or maybe it's dark matter. So the second method that we can use is wavelet transform. So we use wavelet transform. You can use wavelet transform to look for peaks in the data. So you can just think of this kind of like a Fourier transform. You're looking for a large signal to noise sort of ratio where you just see a peak. So as before, if you have these peaks and you detect them, it's clumpy, it's probably point sources. If you have something that looks really smooth, being you don't find peaks, that either means there aren't point sources or they're really, really faint. And they're so faint that you can't tell the difference. You just can't detect them. Okay, so what are the results that we have from these two different methods? So in 2015, two independent groups did use these two independent methods to come to a conclusion that, so there was kind of a consensus on what the conclusion was. And it came back looking like point sources. In that both of these models found evidence for clumpy rather than smooth signals for the galactic center excess. So what you see on the left is from the wavelet transformation, they found some peaks, so these little dots are. And on the right, from the non-Poissonian template fitting, such as putting the different spatial components together and floating them, they found that none of the flux wanted to go into the smooth template. So this was the dark matter template. And that is the red thing that's peaked, pushed up towards the left. And then you see in that orangey yellow, around 8%, 7% of the flux, it all went into point sources. So, and it did that with a very large base factor. So it was very statistically preferred to have the flux go into point sources. So 2015, it was looking a bit like maybe the answer was the galactic center excess point sources. But But 2019, actually, two independent groups, again, different to these groups mostly, use these two independent methods to actually look a little bit more into what these results really meant and challenge their interpretation. So first of all, on the non-Poissonian template fitting, so in a paper I had together with Tracy Slatcher that came out last year, we showed that if you get the modeling of your templates wrong, it can hide a dark matter signal. So we showed this with some proof of principle scenario, just where you had components that weren't quite right, so templates weren't quite right. But I think most importantly, we showed there seemed to be some evidence of something going wrong in the real data. So what we showed was, if you look on the left figure, if we just analyze the data as was done in 2015, we found there was no evidence for dark matter, fine, that's why the dark matter, the reds, pushed towards the left. And the whole of the excess was absorbed by this NFW, or these are the excess point sources. So in the region we were looking at, this is around 2–3% of the flux. But then what we did was we just injected a dark matter signal. So we injected something that looked like the excess that was smooth, and that's the middle figure. So this is about 2% of the flux, roughly the size of the excess. And what happened was the flux just went into the NFW, or the excess point sources, and then dark matter was still heaped at 0. So the fit didn't find the dark matter. Then we kept churning up, putting in more and more amounts of dark matter. And you can see on the right, we injected something that was several times larger than the excess, and the fit still didn't find it, and it still misattributed it to these point sources. Eventually we put enough in and the fit did find it, but you had to put in a lot more before it actually found some amount of the dark matter signal, and even then it didn't find most of it. So our conclusion were that from this paper was that the systematics didn't seem to be under control, because you couldn't find a dark matter signal even when you put it in the data. And really, there was a lot that had to be understood here to try and claim any robust result, either for dark matter or for point sources. We weren't claiming it was dark matter, just that it looked like we don't know what's happening with this method. Just a little bit more information to understand kind of why this was happening. We're injecting a signal and it doesn't find the dark matter. So when we were doing this analysis, you usually have priors that are positive, in the sense that we're doing a Bayesian analysis and you want your priors to be physical. And of course, it doesn't make sense to have a negative dark matter flux, so you just allow it to be positive. And the plot I'm showing on the left here is just that. So the usual analysis, everything has physical values. But we kind of realized that because we were injecting these signals and it wasn't finding it, it seemed like the fit probably didn't want anything that was smooth. And the figure on the right is actually showing that if you relax the priors on the dark matter normalization, it actually then floats to deeply negative values. So you can see that it's then peaked around maybe -8% of the flux fraction. And of course, this isn't physical, it's just kind of a handle on what's happening. But what this shows you is that the degeneracy of smooth signals, being if you have dark matter, or you have really faint point sources that just look effectively like something smooth because they're just so faint. This was not what was explained. That would not explain this behavior, in the sense that the fit does not want anything that is smooth at all. We also observed that the degree of oversubtraction, being just how negative the dark matter was floating, it varied with different diffuse models. So it didn't go to the same negative value for all these different diffuse models. So the effects seemed to be worse in some models compared to others. So we also said the effect likely was due to diffuse mismodeling. Okay, so at that point, it looked like, well, maybe we need to look a little bit more into this method to understand what's happening, but it didn't seem like the evidence for point sources really was robust with this method. And then the really interesting other update was with the wavelet transformation as well. So another group went back and tried to reproduce this result from 2015. And what had happened since 2015 is Fermi had released a new point source catalog. So point source catalog is really just a list of where are point sources and some information about them. So given we had this new information, so Zhong et al. Had done this wavelet analysis and had a look where this new catalog, which is called 4FGL, actually lined up with the point sources that you find in the wavelet method. And what they found, what this figure is showing on the left, well, the only one that's there so far, you see there are these red circles around the point sources that they find, their peaks. The red circles are ones that are part of this new point source catalog. So it turns out this 2015 paper for the wavelets really did correctly find point sources. It found point sources that people didn't know about at that stage. But then the really interesting thing you can do now with this is, well, if these are part of a catalog, you have information about them. So you can have a look in your catalog and see, what are these point sources? Are they something that could be the excess? So it turned out actually, most of these point sources can't actually explain the bulk of the excess at all. So you can see this in that if you just mask all the point sources, first of all, does the excess stay there? If the excess went away, you'd be like, well, I guess these point sources probably were the excess. But what's shown on the right is, so the previous analyses where the excess had been established to exist is this 2FGL mask, that's just a different catalog. So that's blue dashed. But then the orange, this NFW 4FGL mask, that's the new mask. So they mask it and you see the energy spectrum, which is what's plotted on the right here, is still there. But then you could look into the list and just see, okay, what are the properties, which of these actually then might be the excess, and you can just stack them. And that's what's shown in green. So these are candidate central source population members. So you see that even the ones that potentially could be the excess don't have the right sort of normalization. So the spectrum is not actually matching there. So this means the bulk of the point sources that are found with this particular method just can't explain the excess. So that was quite a twist, 2019 for the galactic center excess. So the interpretation of both these papers were challenged, and it seemed like there was really no clear evidence for galactic center excess point sources at this stage. Of course, there are more twists to the story. So just a few months ago, so there was a few different, so together with Tracy Slatcher, and then there was a different group as well that were just trying to follow up to understand exactly what was happening. So this group, so in the paper by Bushman et al., showed that the dark matter injection test issue that I was just discussing earlier was indeed likely due to diffuse modeling. So the way that they showed this was just using improved diffuse models. So there was one new model that they constructed in their paper. And they also did something which was different by using spherical harmonics. So they're doing a marginalization over effectively more degrees of freedom. So because we know some of these models are not working so well, you just break them into more pieces. The template's effectively broken up into more pieces. They all float, and then they have more freedom to kind of get the right answer. And what they showed was that you could explain this kind of deeply negative behavior by just comparing older models with newer models. And the newer models, you don't see this. So the left-hand side is an older diffuse model. What's shown in blue is the dark matter flux. So you can see that it can go up to negative values. On the x-axis is just the harmonic number, so the harmonic number. Okay, so then the point of this paper as well was saying that the point source preference seemed to be robust to the specific variations they used and these different diffuse models. So they still always had some evidence for point sources. But while you can be robust to some particular analysis choices, doesn't mean you'll be robust to all of them. So this is part of the two papers that I had this year with Tracy Slatcher. So we kind of went along a similar sort of direction. We noticed that a lot of these things were going wrong because things weren't being modeled correctly. So we also had thought about just breaking these templates into pieces as well. But we did it in a different way. We tried just breaking the signal template into really basically only just two pieces. So like a north piece and a south piece. And we found that when we did this and ran the fit again, the point source evidence pretty much went away in the region we were looking at, which was a 10-degree circle radius. And not only that, really interestingly, we found that you could get the smoother symmetry that was preferred over point sources in some of the cases. So this is what we had on the right-hand side. You see that the north smooth galactic center excess was 2 times bigger than the south, which seemed really strange. It was strange that just giving the signal model just an extra degree of freedom and then it was just 2 pieces would make the point source evidence go away. But we think we do understand actually why this happens. And it can be explained just by having some unmodeled asymmetry in general. And then you're trying to fit something which isn't quite right. So we actually showed this in simulated data as well. So on the right-hand side, in the top row, I'm showing the real data. So on the left, these are just flux fractions again. And if I analyze the real data with just symmetric templates, so this is the standard sort of older way of thinking about it, you see that the smooth flux, which before was called the dark matter flux, it's called smooth now just because of breaking into a few pieces. But you see it was still on 0, and the GC point sources you detect something. And the right-hand side is just showing you the source count function. What this means is it's really just, so it's a luminosity function, and it's just the number of sources you have as a function of their brightness. So if you're on the right-hand side, you're brighter. If you're on the left-hand side, further along the x-axis, you're fainter. What we found in simulations was if we just simulated the best fit to the real data, which was this north-south asymmetry, and then tried to fit it with the old pipeline, which was just the symmetric point source template, we got something that looked a lot like the data. So you see that the top and the bottom columns look very similar. So we didn't simulate any galactic center excess point sources, yet the fit seemed to think that the point sources are really good there. So it seems like this fit is getting confused if you're just not giving it enough sort of degrees of freedom when you have this sort of mismodeling going on. So note that we weren't claiming that the galactic center excess really is intrinsically asymmetric. One main reason for this was that after we changed the region of interest, the asymmetry wasn't always there in all diffuse models. It was in some, but not all of them. So we think likely this is probably due to mismodeling as well. So we're just not getting the shape of these templates right, and it makes sense that probably then some other leftover sort of asymmetry then is being transferred into the excess template. More broadly, we also realized, and this was discussed a bit more in our longer second paper, that any type of mismodeling potentially might be able to cause a spurious point source signal. And the way you can think about this is just in a really simplified sense. If you have an incorrect model, it can lead to increased variance relative to the data, just because, of course, it's not going to explain the data perfectly. But this is also one of the features of a point source signal. So before I was speaking about you have this extra pixel to pixel variance, you kind of, all these peaks, you're kind of looking for variance when you do this. So statistically, they can look kind of similar, and this can kind of trick the fit into thinking there are point sources there when they really aren't, and instead you just mismodeled something. So it seemed like the systematics still weren't really well enough controlled in this method. So at this stage, we don't think the claimed evidence for point sources is robust. We also don't think it means that it's dark matter. It's just there are some systematics here that we really need to understand before we want to claim anything. Okay, so I spoke about systematics a bit. I want to just take a couple of slides to show you why this sort of thing kind of happens. So a lot of this comes down to the galactic diffuse model. And just to give you an example of how hard some of these analyses really are, so these two methods I spoke to you about before, the template fitting and the wavelets, they're looking for sub-threshold sources. So these things are not very significant if you were to find them. But we find that if you're actually going to use different galactic diffuse emission models, the sort of point sources you can get that are predicted when you use these can vary really drastically. So what this figure is showing, the different dots are different point sources that are detected to 5 sigma. But you see, using different background models give you totally different point sources. So they're found at 5 sigma in one and they're not found in the other one. And you can understand this because the key point really is that really all the diffuse models we have are not good. So even the best diffuse models we have are far from good fits to the data. And you can see this in the figure on the left. In what this figure is showing is if you were to just take the best fit to the real data, even with a good diffuse, what you think is a good diffuse, a better diffuse model, and then you simulate your best fit sort of values, and then you analyze both the real data and the simulated data. So what you should get from the simulated data is what's shown within the bands. What you actually get when you do the real data is shown by this other straight line for 2 different galactic diffuse emission models. These are the ones that make up most of the gamma rays in the sky. And you can see at lower energies where the excess peaks, these are really far from describing the data. So clearly there's some systematic here, and this is one of the key things that kind of keeps playing with these results and potentially hiding what's really going on. So really better diffuse models are key to moving forward and understanding what's happening with the galactic center excess. Okay. So I just want to give you really quick outline of what the current picture is. So I just spoke a bit about some of the updates in terms of our understanding of point sources, if they're there or not, but there are other features as well. So in terms of the morphology, I think this is not robustly known at this stage what it actually is. So there are a few papers recently showing that it might prefer the bulge, which is the morphology on the left, and on the right, the NFW, which is the dark matter sort of profile. So in some of these studies, if you change some of your modeling choices, the preference can flip between a bulge and the sort of dark matter profile. In other ones, this doesn't happen, but then it's also not clear if there are other sort of modeling choices that might change what the result is. So I think we don't know for sure which one is the correct answer at this stage, but it certainly has big implications if we could robustly exclude one or the other. In terms of the energy spectrum, it's still true that it's comparable to millisecond pulsars, but it also can be fit very well with dark matter, particularly for nanolayers to hadrons, but you can have lots of different final states. So both of them kind of work at the moment for that. In terms of the intensity, I think it's really well explained by particle dark matter. in the sense that it's predicted by the thermorelic cross-section. You get something that's kind of approximately in the right sort of range for that. For pulsars, I think there's tension building here on this point, particularly with the new wavelet results, being they don't find these peaks that we expect to be there. So if you don't find them, they must be, if the point sources are really there, they must be really faint. And if they're really faint, you're going to need a lot of them to explain the excess. And we're starting to get into numbers now of at least more than about 5,000, but maybe you need a weird sort of luminosity function to do that. Maybe it's more like tens of thousands or even up to 1 million, depending on how you model this thing. So you're going to need a lot of them. And then you kind of ask the question, how do you get so many pulsars into the center of our galaxy? And these are already pulsars that aren't like things we know. So I think there's some tension building on this point for pulsars. Okay, so moving forward, how do we answer the question? So hopefully I didn't just present too much doom and gloom of systematics and difficulties in doing these analyses, but I think there are definite steps that we can take to try and get to the bottom of what's happening. So first of all, if it's pulsars, we might be able to see them directly if they pulse into radio. So if they give off radio waves, we can use radio telescopes to try and detect them. So for example, we could use MeerKAT or the Square Kilometre Array. The figure on the right is showing potential reach of some that we might be able to find in the galaxy. There's also the question of if you don't find any, does that mean they're not there? Maybe you just got unlucky, maybe they're a different type of pulsar. But hopefully, if they're there, we'll see something. In terms of dark matter, I think probably from the center of the galaxy, people will never be totally convinced that it really is dark matter, no matter what we do. So I think really what you want is you want to see a signal elsewhere that's consistent with what you see in the galactic center. So an ideal place to do this is to look into dwarf toroidal galaxies. So these are really dark matter dense environments, have pretty low backgrounds. And interestingly, at the moment, there's no real tension with the galactic center excess. So the figure on the left is from a Fermi analysis. The sort of circles that you see are potential fits to the excess in different papers. And then their limit is the black line. So it looks like there's still some room there. That said, if the galactic center excess really is dark matter, we probably expect some signals should appear soon. Again, that said, there are plenty of sort of other ways you can get around these bounds. So it won't be definitive, but I think at least if something starts appearing in the dwarf toroidal galaxies, that would be very exciting, particularly if it's then correlated with the J factor. There's also a really interesting paper just this year, so this is the figure shown on the right, that actually these limits from dwarf toroidals can weaken even further once you take into account more of the uncertainties to do with the dark matter density. So in this paper, they were just looking at structure formation models and putting in more meaningful priors, what you might expect for the sort of properties. And they find that actually there's no real tension at all. So far looks like the dwarfs are fine. Maybe we also actually have a signal elsewhere. So there is a excess of antiprotons that's been detected by the cosmic ray experiment AMOS, and it actually overlaps with the GCE. So there's been a bit of debate in the literature if it's systematics or how significant the signal is. I won't discuss that. You can see Tim Linden's talk later today. But interestingly, this can be accommodated with really minimal sort of particle physics models. And it isn't ruled out by collider or direct detection constraints. So for example, if you just have a hidden sector model in one of the really sort of well-motivated scenarios, you can explain this. So the right-hand side is just showing the different dark matter masses and mediator masses. There's a lot of parameter space that's still allowed. The left-hand side is just showing for a 2-to-2 annihilation that we clearly have some overlap. Okay, other avenues to try and understand what the excess is. One thing we could do is looking in a little bit more detail at the energy spectrum. So the systematics are large for Fermi, below around a GeV, but the energy spectrum for pulsars and dark matter differ a lot in this sort of sub-GeV, GeV regime. So if we use an MAV gamma ray telescope, this might be able to shed light exactly on what's happening here, and that should actually be happening in the future. So we have potential telescopes like MIGO, Neastogram. Other avenues as well would be thinking about different ways to do these fits. So of course we have a lot of issues with systematics in trying to understand what the excess is. So ideally, if you can have some sort of complementary handle on what the systematics are, maybe we can understand or learn a little bit more about what it could be. So an example of this recently was just using machine learning, so training neural networks on the Fermi data. Florian List and others just very recently actually found a smooth galactic center excess preference. So I think that's very interesting. It's a preliminary study, being it's one of the first few studies, so I think this is going to be very fruitful moving forward to see what happens here. We could also have better measurements of the dark matter density, so we have a lot of uncertainties from this, but Gaia should be able to do this. And I think really importantly, we need better diffuse models, just because everything we have at the moment is really not so good. Okay, so just to summarize, the excess is firmly detected. It seems to exist. We don't know what it is, and it's been very controversial as to what it might be or might not be. A really exciting possibility is we are seeing the first evidence for annihilating dark matter. And I think there are a lot of arguments for this, in that the signal has a lot of consistent features of what we would expect for dark matter. I think for the leading alternative pulsars, the main argument we have is the energy spectrum, and hopefully we can learn a little bit about how this looks compared to dark matter with these MEV telescopes. I think there are also mounting arguments against this, in the sense we're not seeing any of these pulsars in any wavelength. So maybe we should have seen them in the wavelet analyses. It seems like you have to have a lot of them now to not have shown up there. And then there are questions of how you just get so many pulsars in the galactic center. Maybe it's doable, but it seems like a lot. So really, if the excess does arise from pulsars, it must be very different to the sort of the type that we know that we have in the Milky Way already. So we discussed a bit about the previous point source evidence and how those sort of results have been challenged. So it seems like there are a number of systematics that we have to understand with the non-Poissonian template fitting. Particularly, we showed with these unmodeled asymmetries or just general sort of mismodeling, it's possible to produce spurious point source signals. And the new wavelet results show that the previous band point sources are actually not the bulk of the excess. So this is something we want to get to the bottom to, and I think there are a lot of ways forward, particularly these complementary searches for both dark matter and pulsars, and hopefully improving the modeling in the future. But for now, the puzzle definitely continues. Thanks.